Right. So I'm Lynn Chikosha from Universal Matter, and today I'm going to be speaking to you about how we're using our graphene and our carbons to decarbonize. Okay. So we have three locations at the moment where we're based. Our headquarters are in Canada, in Burlington, Ontario. We have a plant there, which was commissioned 2-3 weeks ago, where we have the capacity to make a ton of graphene a day. We have about 20 staff, but that number is growing because the plant is now live, so we're continuing to recruit more team members to support that activity. We also have application development activities there, centered around concrete and cement, and a little bit around asphalt. We have a subsidiary in Houston, Texas, and here we've got about 9 staff at the moment. They do a little bit of our pilot production of our graphene and related materials, and also have an application development lab primarily focused on tire and rubber applications. I'm based at our UK subsidiary, UK, which is in Redcar, as well as my colleague Andy, who's sitting over there. We used to be Applied Graphene Materials. We were acquired last year by Universal Matter. We have a graphene production plant. We also have a graphene dispersion plant at the same site. We have about 20 staff. I think that number might be a little bit higher now, maybe 23. Again, we're continuing to grow as a company, so between 50 and 55 team members. So what is our vision as a company? Our goal is to produce high quality and economical graphene from simple carbon feedstocks that dramatically reduce our carbon footprint so we can use carbon to decarbonize. So I'm going to talk a little bit about our technology, and we have graphene and we have related advanced materials. So historically, we have our graphene nanoplatelets, which are manufactured using the heritage applied graphene materials process, which is a bottom-up synthesis method. While the quality of this material is quite high, the process is quite energy intensive. We get a graphene nanoplatelet which is very thin and crumpled, and it's about 5 to 10 atomic layers. It's very low density, it's got a high surface area, and it gives us very good corrosion prevention. In 2018, Rice University developed a method for preparing graphene from a flash Joule heating process. So effectively, you can use any carbon feedstock. So you can use coal, biomass, rubber tire, carbon black, so recycled tire carbon black as a feedstock to go into that process. You apply a short electrical pulse, and you get a hexavalent carbon graphitized structure at the end of that. The flushing of the carbon feedstocks produces a primary nanoparticle which has a graphitic skin core, and you can have an amorphous core structure in the center. Obviously, depending on what feedstock you put in, you can get a range of morphologies, so there's quite a range of advanced materials that you can get from this process. This is one of the materials that we get out of that process. We call this one a polyhedrographitized carbon, which has an onion-like structure. It's a very small particle size, but it has a large structure, and it forms distinct graphene layers in the onion-type structure that we talked about. I'm sharing this particular structure because I've got some data that is specific to this material. Obviously, there's a lot of materials that we get out, so I won't be able to go into all the details of the materials that we produce. So what are the benefits of the flash Joule heating process? We get high quality materials with a few layers. We've got a range of morphologies, both in flake or polyhedral structures. It's economical because it's a very efficient production process. It's quite quick, and it's also highly sustainable. So the process is energy efficient. You can use waste, recycled tire carbon black, as I mentioned earlier, or other carbon feedstocks. I'll touch a little bit about our Genable trademarked dispersion technology. So one of the key things with using graphene is that you have to get the dispersion right if you want to realize the benefits of graphene in your application area. So what we do as a company is we've spent a lot of time developing our dispersion range, and we've got a range of graphene dispersions that are formulated to the optimum particle size to make sure that you get the performance benefits that you need. They're at the right concentration relevant to the application that you're looking at, but also they are stable in can, so they don't re-agglomerate. We make sure that we've tested them in-house so that we've got a minimum of at least 3 to 6 months in the can, as opposed to if you just put graphene, say, in water, it'll be stable for maybe a day, a week maximum. So we spend the time kind of optimizing that so that when you put it in, you can get the performance benefits that you're trying to realize. For the eco-friendly or environmentally conscious formulator, we've got a range of eco-friendly dispersion matrices that we use. So we're using water-based dispersion media, so you can have graphene or our advanced materials in a water-based dispersion. We also have some solvent-free epoxies, polyurethane matrices that you can have, but we also have renewable bio-based resins that are available to those formulators who are conscious of their environmental impact. So I'm just going to focus on coatings for a moment. We are active in quite a few areas, but at UK in the UK, we're focused on coatings applications. So I'm going to talk about the performance benefits that we get in coatings. So with our graphene nanoplatelets, we get really good barrier properties. So we're able to achieve anti-corrosion, water barrier, chemical resistance. We get anti-static dissipation. We get electrical conductive coatings as well. With the polyhedral graphitized carbons, such as the PGC18 that I showed earlier, we're able to get really good mechanical enhancement. So we get good abrasion and impact resistance. We get good tensile strength, good elongation. We also see anti-static dissipation and electrical conductivity in coatings. So a couple of examples of some performance enhancements that we've achieved in coatings. So if you're looking at barrier property enhancement, this is looking at water vapor transmission rates. So in this particular example, we're looking at a fully formulated epoxy coating. And initially, we started with the commercial micaceous iron oxide primer, which has 40% mica. And we took out that mica, which is that red line at the top, and we can see that the water vapor transmission rate increased because the mica is a plating material, gives you good barrier properties. We then replaced the graphene, we then put graphene in to that red primer control at the top. So we put 0.05% by weight of graphene, and we can see there's a significant reduction in water vapor transmission rate, so 45% reduction compared to the control. So even though you're using significantly less by weight of the graphene, you're still able to actually improve the performance over the existing commercial standard. Furthermore, because you're only using a small quantity of graphene and you've taken out a lot of the fillers, in this case the mica, you actually get a coating that has better secondary properties such as good adhesion to the substrate. So it's a more flexible coating. Because we get these really good barrier properties, you can extend that into anti-corrosion performance testing. So if you look here, zinc phosphate is used quite a lot in anti-corrosion applications. In this particular case, we tested 8% zinc phosphate in a 2K epoxy primer, and we saw by 720 hours, we were seeing blistering and rusting on the control, but the equivalent graphene system with only 0.05% of our AGMP35, the graphene nanoplatelet, was showing no signs of blistering and no signs of corrosion. And again, you can see when we get to 1440 hours, both the GNP and the PGC are not showing any signs of blistering or of rusting compared to the zinc phosphate. So effectively, you're able to replace the zinc phosphate with a much lower loading of the graphene and the related PGC. The loading level of the GNP in this case is 0.05. For the PGC, we're using 1%. So again, you're getting performance with 1% PGC versus 8% of the zinc phosphate. We then moved on to look at chemical resistance. Again, we wanted to understand if the barrier properties that we'd achieved or we'd seen in water vapor transmission rates and in anti-corrosion performance could be translated into chemical resistance properties. So we tested immersion in lactic acid and sodium hypochlorite for a period of 28 days, so kind of a half immersion in both of those media. And again, we saw significant improvements. So we were comparing to glass flake, which is used in this application, 20% glass flake. And after a few days, we started to see some defects coming through on the glass flake systems, which weren't necessarily appearing on the graphene enhanced systems. So again, if you look at the lactic acid panel, you can see on the glass flake panel that the substrate underneath, so the steel underneath the coating, has started to degrade. The coating has degraded completely, and you're now affecting the substrate underneath it. Similarly, with the sodium hypochlorite systems, the coating was completely degraded, and you actually had rust off the substrate because the coating had completely degraded. Whereas with the graphene, we're just seeing a little bit of surface discoloration, so the coating is still intact. So effectively, you get much superior performance with a small percentage of the graphene. So in these cases, the 5% enable 1200, which is the dispersion, translates to 0.05% of graphene and 0.1% at 10%. So again, significantly low loadings of the graphene is giving you superior performance. There's still a lot of reluctance, even though we see these improvements. The coatings industry particularly is very conservative, very traditional. They don't want to move away from the materials that they've always used. But there is also, in addition to the performance benefits that we've just talked about, there is also a sustainability need to move away from some of these materials. So if you look at glass flake, it's associated with the use of with the development of acute silicosis, especially for the people who are involved in the mining. And also if you look at the energy intensity of mining aluminium to get your aluminium flake, it's a very energy intensive process. So again, it's to get 1 ton of aluminium requires 15 megawatts of electricity, which is equivalent to a 2-person household in 5 years. So effectively, the energy use is quite high. So actually moving to something like graphene can be sensible both from a performance and a sustainability point of view. Again, there's a lot of media attention to PFAS, polyfluoroalkyl substances, which have been used commonly to improve things such as abrasion resistance. There's a lot of ongoing research into the negative impacts on human health associated with the use of PFAS materials. So there's reproductive effects, such as decreased fertility. You get developmental effects in children, so low birth weight, accelerated puberty, and also you have an increased risk of some cancers, including prostate cancers and testicular cancers. So actually, if you use one of our PGC, so here we're using the PGC 18 that I showed earlier, and at 0.1 and 0.5%, we're able to get up to 40% improvement in abrasion resistance. We see up to 50% improvement in abrasion resistance, in impact resistance in the same polyurethane system. So there is potentially a safer alternative by using these PFAS materials, by using our polyhydrographitized carbons instead of PFAS. You could have something that is safer without compromising your performance. In fact, you could get much better performance with these materials, but also move to something that is safer. Moving away from the lab, so it's very easy to get good data in the lab, but we want graphene to be something that people associate with real-world applications. There's a lot of papers and lab work that has been done, but we're taking these out into the real world. So we've got a couple of case studies. There's a narrowboat that we painted, I think, 3 years ago. Initially, we did a small test patch that was 1 square meter, and then we did an inspection after 6 months and 12 months. The owner of the boat was really happy with the improved performance that he got with our paint compared to the existing commercial system. So after that trial, we've painted the whole hull with our paint, and that's been on that hull for, I think, two years now. And then similarly, we had a collaboration with the Environment Agency, where we painted some floodgates with our primer, because they were looking to move to more sustainable materials that give you a longer lifetime, reducing your maintenance intervals. That's been on for and also a couple of years. So the primer is graphene enhanced. There's a top coat on there. We periodically go and look, and it is performing better than the existing commercial systems. So again, this is just demonstrating that this is beyond what you just see in the lab. There is real-world applications and benefits being realized. So going beyond coatings, so a lot of this work is being carried out in North America. So in terms of rubber and tire, we're seeing improvements in things like abrasion and tear resistance with greater than 20% improvements. This is one where we're using recycled tire carbon black. So you take old tire carbon black, we flush it, we produce advanced materials, and then it goes back in and you get better performing products. So the partners that we're working with in this application are really happy with the enhancements that they're seeing. Similarly, in asphalt, we have a graphene polymer composite that we've developed for this application. It's pre-dispersed into polymer pellets, and we're seeing improvements in micro-cracking and reduced development of potholes, and it doubles the life of the road, yielding increased pavement resurfacing intervals. So effectively, again, from a sustainability point of view, it's better because you're extending the lifetime of your system. In terms of concrete, we have Genable Decarbonizer, which is a ready-to-use graphene-based liquid admixture, which has been developed to enhance the strength of mortar and concrete. And again, we've seen improvements in compressive strength, so up to 36% improvement after 28 days. But you can see that the early strength development is a lot better than the existing system. Again, this is one where we're looking at improving the strength of the material, so you're using less cementitious material, thereby improving your environmental impact. So to summarize, the flash Joule heating process is a more efficient method of making graphene and related advanced materials. We have a dispersion technology that is safe and easy to use and environmentally friendly. The other thing that I didn't mention, it's very easy to incorporate into existing processes. So if you think about this in terms of paints and coatings, you don't have to change the dispersion mills that you're using. It's very typical practices. So once we've developed the dispersion, it's easy to incorporate into existing systems. And overall, we get outstanding performance improvements that enable extension of life, reduced maintenance requirements, and lower environmental impact. Okay, any questions?
Excellent presentation, Lynn. Thank you very much. Can we take some questions, please? We have one.
Thanks for the nice talk. Just a comment more than anything else, coming from a coatings background.
Okay.
It's selling paint is a volumes game, right? So
Yeah.
it becomes essentially like a commodity.
Yeah.
One of the most price-intensive component is additives, selling for about $4,000 a ton.
Yep.
So just being a bit mindful, having something in there. The customers want everything, but when it comes to actually price, they beat you down for it. So just something to be a bit mindful of.
Okay. All right. Thank you.
Any other questions for Lynn?
Yeah, I have a question. Lynn, thanks for the presentation. I guess the key question is this feedstock.
Yeah.
You know, about consistency and variation of feedstock. How do you ensure that you get a...
So we do a lot of pre-treatment to make sure that the feedstock as it goes into the flash process is within certain control limits. So for instance, if you take the recycled tire carbon black, we have specific partners that we work with in terms of getting that feedstock in, and then we check the quality of that feedstock before we put it into the flash process, and then but also the process sublimes out a lot of impurities, so we get a pure material at the end. Yeah.
Any further questions? No? Okay, thank you very much to Lynn. Thank you very much.